All right, here we go. Let's break into calc. I want to get through this so you guys can have an unfettered work day tomorrow. But we got to get through a few things for that to happen. So let's look at a couple problems here. So how about I can skip that one. Let's do this one. Let's do this one. I'm going to add one little question to this. So reduce, I love physics even more than calculus, so we're going to do a little physics here. But this is good calculus physics. So to estimate the height of a building, a stone is dropped from the top of a building into a pool of water at ground level. How high is the building if the splash is seen 6.8 seconds after the stone is dropped? Well, we're going to need this equation to do that, right? Was it in meters? No, seconds. So we can make our answer in meters. So here's the function that we're always going to use for, we call it free fall problems, where an object is just, the only force acting on it is gravity, right? So if you're in physics, that ought to look pretty familiar, right? So here's the formula. S of t equals negative 4.9 t squared plus v naught, what's that? Initial velocity times time plus s naught. I don't need to blow my nose. What is that?
That is the initial position.
Initial position, okay? So if we're trying to solve for initial position here, right? Everybody agree? Okay. What are we doing? What are the parameters? So we're going to read this problem, and you got to tell me what numbers to plug in where, based on the problem. There's a bunch of stuff that's implied by this problem. So when they say it is dropped from the top of a building, what does that imply?
Initial velocity 0.
Initial velocity is 0, because I'm just doing that, just dropping it. So we start the videotape when I open my hand up, right? So the thing is just at rest and it starts to fall. So that's telling us right here, dropped from the top of a building, that's telling us that V naught equals 0. Okay, what else is it telling us? 6.8, right? What's that?
That is the time, the last time.
Time is 6.8, right? So in other words, always, it makes physics so much easier if you think about it like a video, where every frame in the video is a moment in time, right? So when the stone hits the water, if you look at the little, how it counts the little seconds at the bottom of the video, it says exactly 6.8, right? Okay, there's something else here too that we also need to identify. There's something else implied by some wording here that's really important.
Acceleration is due to gravity.
Okay, that's already kind of given to us right there.
Initial position is the height of the building.
Zero. Okay, ground level. It falls into a pool of water at ground level. What's ground level? 0, right? So that's telling us that S of t equals 0, right? Does that make sense? So, and we know what t is. T is 6.8. So if we're trying to find, we want to know how high is the building. Well, how high is the building is really just, new color. How high is the building? That's the initial height of the rock, right? So that's really what we're solving for. Okay? Make sense? So if we plug all that stuff in, what do we get? We get 0
126.576
equals negative 4.9 times 6.8 squared plus that whole thing just goes to 0, right? Plus S naught, which is what we're looking for, right? So that's pretty easy to solve. That's just a, plug some stuff in my calculator. What do I get?
This number.
That number. Okay, so we get the number.
226.576.
Say it again.
226.576.
Right, and what are the units going to be?
Meters.
Meters. Okay, that's not a good enough question, though. I would have asked a little more to that. I would have said, how fast is it going when it hits the water?
Okay, anything you take.
So Now, everyone pause for a second and think about that. How are we gonna answer that question? So if we add the additional question here.
V1 equals V naught plus acceleration times time.
Okay, so let's take,
Yeah, so he wants us to do it's not the easiest way possible.
well, this is, watch, this is gonna give you the same thing, watch, you'll see. Okay, let's take that free fall equation, and this is, you're not gonna do this, it's not a calculus-based physics class, you're not gonna do it this way, but we can. If I wanna come up with the velocity function, what's the velocity function here? This is where rates come in. Velocity is what? Raise hands, what's velocity? Somebody help me out. What's velocity? It's a vector, okay. It's a vector. It's velocity, the definition of velocity, I'll start you off, is the rate of change of position with respect to time. Now, in physics and in real life, a lot of times, if we just say a rate of change and we don't say with respect to, what's probably implied by that? Time, because it's 99% of the time, we're measuring the evolution of a system in time, right? So it's the rate of change of position, so V of t is S prime of t. Well, what is that? What's the first term give us? I can just differentiate this term by term. What's the derivative of the first term? Does that look familiar? And it does. What about this term? Plus V naught, right? That's a constant. Derivative of t is just 1. And then the derivative of S naught, 0. That looks pretty familiar. Right now, recognizing that the acceleration of gravity is negative 9.8, you have that equation in your physics book, I guarantee it. Right? Okay? So all we got to do then, we know the time was 6.8. So if we want to know how fast it's going is just V of 6.8, or S prime of 6.8, which is negative 9.8 times 6.8 plus, that's just 0, right? And so what are we going to get? Roughly negative 7. Negative 60 something. Can we help me out? What is that? 9.8 times 6.8?
66.64
Units?
meters per second.
Okay, we're measuring distances in meters, time in seconds. Meters per second. Okay, let's talk units for a second. Got some good questions about that. If I'm doing a rate of change, like let's just say that we're doing, I kept getting those examples from the other day. What if we did an example the other day of rate of change of volume with respect to radius, didn't we? Something like that? So you guys tell me then.
No, it was in respect to circumference, wasn't it?
Okay, we could do that too. We'll do them both. If I'm doing dV dr, we could call that V prime of r if we want to, but if you think of it this way, it really helps with the units, right? If you think about the derivative in differential form, right, where it's written in as a ratio, right? What would the units of that have to be? It's going to give me some number. What are the units of volume? If we're talking meters, it would be cubic meters, units of radius.
Meters.
So cubic meters per meter. So it actually works out to be meters squared, right? The rate of change. Does that make sense? Okay. If we were doing, the other day we did one like, I mean, you can get weird stuff. Like, I'll probably erase that example. I think I did. Yeah, I did. But we did like inventory, I mean, you can get really bizarre examples, but if you write it as, what did we have yesterday? DQ, DC, DQ, something like that. What was it again?
1,008,000 over Q plus.
And what were the two variables? Like one of them was cost and one of them was number of items or something, right? So let's just say, wasn't it like, was it DQ, DC, or DC, DQ, right?
Yeah.
I think.
It went up to 351.
Right, so that's right, so we did an example where it was DC, DQ, and C was a cost, and Q was a number of items, right? So that's gonna give us some number, but the units are gonna be dollars per item, right? Those are the units of the derivative, okay? All right, shifting gears, let's take a look at just a couple of these. Now, I wanna make a point with this. We went away, we talked about this earlier. You guys have gotten pretty good, and we'll do more of this. I'll come back to this again and again. I gave you functions, and you told me what the graphs of the derivatives look like. The next thing we'll do with that, as we get a little further into the rate stuff, is we'll apply that to physics. And there's some really cool stuff that comes out of that when we look at the graphs of the kinematic quantities. The graphs of position and velocity and acceleration, there's some very interesting relationships there that tell you a lot of information. So we'll kind of plug that in a little bit by bit, okay? Let's go back to this for a moment, though. So velocity is the derivative of position, right? So in other words, I just gave you here a derivative function, and we're going to work backwards. This time I want you to take the shape of the derivative function and come up with the shape of the function whose derivative is represented. We're going to work backwards. I give you derivative, you give me original function, okay? So we want a position versus time graph that matches this one, okay? So it looks like there's really only three interesting things going on. There's three parts to this story. From 0 to 4 seconds, the velocity is 30 meters per second, right? Then what? Goes to 0 for 2 seconds, and then it goes to 60, right? Okay, so I want to know, what does that look like in terms of a position graph?
It's
So
gonna
it's-
be a slope of 30
Okay,
for 4 seconds, and then it's gonna level out to a slope of 0, and then you're gonna get a slope of 60.
okay, now we got to be careful with the units here, right? And this is something else I want to, this comes up a lot. So what are we measuring velocity in on the vertical axis? Miles per hour. What are we measuring time in? Okay, right? So that's, you got to be really careful with that. So if the velocity is 30 miles per hour over a course of 4 minutes, how much is the position going to change? In physics, we call that displacement. What's the change in position going to be, or displacement? If it were 60 miles per hour, how far are you going in a minute?
2 miles in 4 minutes.
Okay, so normally you go a mile per minute at 60, right?
Yeah.
So if I'm only going 30, I'm only going half a mile every minute. Does that make sense? So in 4 minutes, I'm going 2 miles. So I could do something like this then, right? If we're going to measure position on the vertical axis, if we're going to measure position in miles, and down here we're just measuring t in minutes, I could do something like connect the point at 0, 0 and the point at 4, 2. Everybody agree? Something like that? Okay? So, oops, I gotta start. Oh, whoops. Hang on. I'm going by 2s. So I gotta go between there and these are just gonna go by 1s. How's that? And these are going by 2s, right? So that's 2, 4. So it's going to look like that. Okay? Good. Now what? Between 4 and 6, it should be. Okay, so what does that mean? I'm not going to say anything. You tell me exactly what to draw here. Okay, so I'm going to go over to here, and the suggestion is I just go straight across. Okay? That's what you're saying, right? Okay. Everybody agree with that?
Yes.
Wait, why? It was slope 0.
Slope 0, right? So if the value of the derivative is 0, the slope of the function is 0, right? Okay, and then what? from 6 to 10, we're going 60 miles an hour. So that's where we're increasing by a mile per minute. So in 4 minutes, I'm increasing by, okay, so I guess I gotta go, I gotta add another line, don't I? All right, so we've gone from there up to about there-ish. Okay, agreed? Okay, good. Is that a unique answer? Did we come up with a different answer?
You can have one, negative one.
Ah, good, right? I could. Oh, I can't do it. Anyway, yeah, I could scoot the whole thing up and down, couldn't I? Right? We just arbitrarily chose to start at 0, which probably makes sense, right? Why not start the trip at 0? But I didn't have to. Instead of starting here and going in the positive direction, I could have started down here somewhere or up there somewhere, right? That's an important point. So think about that. When I'm reversing the process, I'm starting with a derivative and I'm writing the function, right? I don't know anything about where it's located vertically. All I know is that this slope is 30, that slope is 0, and that slope is 60, right? Everybody get it? But it might have started here. It might have started here and done something like that, or it might have started way down here. You don't know, right? Those are all possibilities, okay? How could I pin one of those down? Well, what would I have to include in this problem in order to be able to say, okay, it's the blue graph and not the orange one or the green one? I'd have to have something else going on here. I'd have to have some other information. I'd have to say, okay, well, the initial velocity we know is 30, but I'd have to say the initial position is 0, or the initial position is this, or the initial position is this, right? So we're going to come to call that. Later in the year, we'll call those initial conditions. We have to specify some initial conditions that would pin down one of these trajectories. The word we'll eventually use is a trajectory, a family of curves. But I'm just giving you the idea for now. We'll build on this throughout the year. Okay? All right. So there's what we just did, right? Okay, I want to do one more of these before I jump into just kind of a new derivative rule to show you. And that's very mechanical and simple. But it's just, this is bigger. This is important. What I want you to do here is more physics. Newton's law of cooling. I want us to write an equation that represents this. Later on in the year, we'll come back to this and we'll do more with this very equation. So what's this say? Law states that the rate of change of the temperature of an object is proportional to the difference between the object's temperature, T, and the ambient temperature, T sub A. So the temperature of the environment it's in. Okay? How are we going to do that? This is a skill that you need to develop, right? So let's turn this into an equation. So let's highlight some important parts. You see, tell me one thing, Tyler, that's going on up here.
Delta T.
Delta T, okay, proportional to the difference between the object's temperatures. Okay, so we got a difference there. That's a delta, isn't it? Right? We could call it, how are we going to write that? The difference between, let's take this part right here, and we'll write it in green. How do we write the difference between the object's temperature and the ambient temperature? Yeah, right. T minus T sub A. Everybody agree? Differences mean I'm subtracting. So the green part is going to be T minus T sub A. Okay, what else? Okay, rate. Rate is a big word there, right? The rate of change of temperature. Okay? So what's that mean?
Change of temperature over time.
Okay, the change in the temperature over time is going to be proportional to the difference in temperature. So the rate of change of the temperature, they didn't specify with respect to something, so what is it? Time. Right, so we're going to get, there's a dt. Illustrates another point. Case is important with variables. This happens all the time. You can't, I mean, you can't be in the habit of, sometimes people like to write in uppercase or lowercase exclusively. You can't do it in math, in physics, because capital T is clearly temperature and lowercase t is clearly time here. They're very different things, right? What about this part? Is proportional to. Okay? So the proportionality symbol is that, but we can't really do much with that. Let's write it as proportionality, but we got to make this an equation to really do something with it. So if the rate of change is proportional to the difference in temperature, we'd write the proportionality like this. That literally says the rate of change of temperature is proportional to the difference in temperatures, right? But we don't want to, proportionality is weak. We can't do any algebra with that. We're going to make it an equation. So how do we say something is proportional with an equation? If I want to say, let's take a slightly different example, an easier one. If I want to say that y is proportional to x, how do I write that? Y equals, well, that's an example, but that's not a general way of saying that.
Y equals AX.
Okay, A usually will say K. What do we call K? Constant of proportionality, right? So K would be the constant of proportionality. And this is kind of a pre-calculus review, but it's, you don't use this a ton in pre-calculus, so we want to see it here, right? So what if they're proportional? Think what that means. If x doubles, what happens to y?
It doubles.
If x is increased by a factor of 7, y is increased by a factor of
7.
If x is cut in half, y is cut in half, right? But what's the relationship? How big is any x compared to any y? That's what the k tells us, right? Like if we have the equation y equals 10x, then y is always 10 times bigger than x, but they still act proportionally, right? Okay? So how am I going to apply that to this situation then?
We're going to say U of t over U of t equals k t minus t
Times the quantity,
the quantity.
t minus t sub a, right? Okay, that's it. That's Newton's law of cooling right there. And it says everything we needed to say. The rate of change of temperature is proportional to the difference between temperature and ambient temperature. Okay. Later on, we'll do stuff with that. Very soon, we can do some really interesting things with that, and we can do some related rates problems where we can make some predictions. So we'll come back to that. I want to do it. It's interesting to talk about. For today, though, let's take a look at some new stuff. So this is not hard stuff, but it gives us a lot of capability to do more calculus. So 2 rules, product rule and the quotient rule. I gave you 3 versions of this. The first version is the version from the online textbook, and it's pretty good. Second version is from our actual physical textbook. Here's the version I strongly prefer. How come?
It's simpler.
So simple, right? What does the product rule say? The product rule just says, let's look at this one for just a second. If I'm going to take the derivative of a product of functions, right, how do I do that? Well, there is a rule for that. The derivative of the product of f of x and g of x is just going to be f of x. So say the first function times the derivative of the second, plus the second function times the derivative of the first. Okay? So the best way to express that, the most compact and easy way to express that, is like this. We're just going to say that u and v represent functions of x. Could be trig functions, might be algebraic functions, who knows? Those are just some functions, right? In this case of x, because I'm differentiating with respect to x. If that's the case, the derivative of the product of u and v is just u v prime plus v u prime. Well, what's v prime? Derivative of v. What's u prime? Derivative of u, right? Very simple. This is a really easy one to use because the 2 terms are added, and addition is commutative and associative. I can transpose those terms and it makes no difference to the outcome. It's going to be right no matter what because you're adding the terms. Some people prefer to put this term first, and I like this term first. But Doesn't make any difference. Let's try this. Like, what if we want to do this problem here? Okay, what's my u?
3x minus 2x squared.
Sure, right? That's the first function. So this is u. What's v? Right? 5 plus 4x. Okay, makes sense? And so if I want to, if that's what h of x is, it's the product of those two things, then h of x, h prime of x, sorry, is just going to be, well, you use the rule, uv prime plus v u prime. Okay. Now the way I like to do this, it's worked well for me, is to write derivatives in red and non-derivatives in black. And then you kind of see how the algebra works. So what am I going to do here? What's u?
3x minus 2x squared.
Okay. Somebody different. What's v prime? Ryan, what's v prime? That makes sense?
Right, yeah.
Yeah, if that's v, then that's v prime, right? Okay, plus, what is v? Well, there's v, right? So v is just going to be 5 plus 4x. Katie, what's v prime? Or u prime? Katie, what's u prime?
What, 3 minus x.
Good, done. That's the product rule, right? From here, the calculus part is done. Now it's just some cleanup, some algebra, right? So I would just distribute the 4, FOIL this out, and combine like terms. Yes, sir.
So what's the stopping point?
What a great question. So my point, I was about to say the very same thing. So my point here is, if you've got polynomials, did this really make sense to do? It's no easier, maybe harder, than it would have been just to expand this out and get a single polynomial, which is so easy to differentiate, right? I would say that probably in these cases, you're better off just expanding first, pre-writing, and not using the product rule. Great point. Okay, but what about a problem like that? No, I don't have that option, do I? Right? When I'm differentiating this one, I have to use the product rule. I don't have a choice because I cannot combine those any other way. Okay? So let's try this one. So what's our rule? Product rule? Derivative of u times v is prime plus, everybody get v prime, there we go, v u prime. Okay, so we get u is x. What's the derivative of the second factor, v? E to the x. Plus the second factor, e to the x, times the derivative of the first, which is, okay, so there's my answer then, very simple. X, e to the x, plus e to the x. If I want to, I could factor out an e to the x and write it like that. Kind of optional. Okay? No big deal, very simple, right? But otherwise, prior to today, as easy as that was, we couldn't have done it. But you need the product rule for that. Okay, what about quotients? Unfortunately, quotients are a little tougher. I'm just going to skip down to this version. It's a lot easier, right? So if we're taking the derivative of the quotient, so u divided by v, the derivative of u divided by v is always going to be v u prime minus u v prime over v squared. There's a couple ways that people would remember this. Like you could do if u is high and v is low. The derivative of a quotient is low d high minus high d low over v squared, over the bottom squared. You always end up with whatever started on the bottom gets squared on the bottom, right? So one rule, one way to think of it, low d high minus high d low. Okay. This is what the top looks like. Now, this one is critical. You have to get it right, though, because I'm subtracting the terms, and subtraction is not commutative. You can't, if I commute a difference, I get different answers. 7 minus 4 is not equal to 4 minus 7, right? So we have to do this one right. The way I remember it is, and I'll just always remember it this way, u prime is du dx, right? So a short way of saying that would be du, Like when you get in college, you just say VDU minus UDV. And the D just means derivative of, right? So VDU minus UDV, well, VDU sounds like video. And I just always remember it always starts with video. I just think of it, there's a song out there. I've never seen it. So that's what pops in my head. That's how I remember it, okay? So video minus whatever the other one is, VDU. But whatever way works for you, I don't care. You find a way to remember it. But let's apply it, okay? So there's our quotient rule. This time I am stuck, right? This is not one I can do. I mean, I probably could, actually. I probably could break this up into partial fractions and do some stuff, but it's starting to be more work now. Now we definitely just want to use the quotient rule. So let's apply this. Y prime equals, now what's my rule? Which one's x, or I mean, obviously, which one's u to start with? Top one, v is the bottom one, right? So v du, the low or low d high, or sorry, high d low. No, low d high.
What?
No, high d, what is it? Low d high. I never remembered that one. I got to think about it. That's not the one I use. Low d high minus high d low. That's it. So low d high. There we go. Low d high. So the low is going to be this one, right? There's v. I think v to u. D high. What's that going to look like? What's u prime?
Uh,
5, right? Good. Derivative of the top is just 5. Minus pi d low. What's the derivative of u?
X.
2x divided by v, or low, squared. Calculus is done. Now you're just simplifying. So what would we get? If I distribute, I'm just going to get 5x squared plus 5. If I distribute, now here's how I would do this. You know you're going to get a negative 2x that's being distributed, right? So if I distribute a negative 2x, what am I getting?
negative minus 10x squared minus plus 4x.
Plus.
4x.
All divided by that.
X squared plus 3x. X to the 4th.
Okay, but do we want to FOIL out the bottom?
My God.
No. No, we want to, our goal is, we don't want to expand stuff in calculus ever. Right? We want to leave it factored, because think what the kind of stuff we're going to do with this. The kinds of things we're going to do with the derivative is we're going to ask things like, where are the zeros of the derivative? Well, we want to factor for that, right? We want to know where is the derivative undefined, where the bottom is 0, right? So you always want to leave things factored. Don't undo all that good work that you've already done there, that you already start with in a good place. Don't mess it up. Leave it factored. On the top, if we combine like terms, what do we get? Negative 5x squared plus 4x plus 5. All divided by the quantity x squared plus 1 squared. There you go. That's your answer. That's a good answer. Okay? Okay, we're going to try some, I'm going to look at some here now where the goal, and this is really important, the goal is to avoid using the quotient rule. It kind of sucks. It's a hard one to apply. There's lots of stuff going on with the quotient rule. Right? That is not really very pretty. There's lots of derivatives and there's quotients and things going on there. It's kind of a mess, right? It's the one we'd really like to avoid at all costs if we can. So can we rewrite this in a way where we do not need the quotient rule? Yeah, I mean, well, I can't, multiplying by 6 would change it, but what you probably mean by that is factor out the 6. It's a constant, right? The 6 on the bottom, the quotient rule means, do I have a quotient of functions? No, I don't. I just have a constant on the bottom. I do not need the quotient rule. Would it work? Yeah, it would, but it's a lot of extra work to apply it, right? So we'll just rewrite this as y equals 1/6 times x squared plus 3x, easy, right? Now what's my derivative? I've got my 1/6 out front that I'll leave there. What's the derivative of 2x? Or, sorry, x squared, whoops. 2x. Derivative of 3x? So to simplify that, all I'm doing is just distributing the 1/6 and getting, yeah, just x over 3 plus 1/2, right? Much easier. You want to pre-write that. How about this one? We won't even do it, it's so simple, but how do I avoid the quotient rule here? It looks like a quotient.
1/8 times 1/8 times 1/8 by x to the fourth.
How about just 5/8
5/8.
x to the 4th? Simple power rule, right? No big deal. How about something like that? Let's talk about this one a little bit. So I could factor out an x, good. So I've got y equals negative 3x times what? On the bottom, I've got a 7x, so what happens? Cancel x's, and so this just becomes y equals negative 3/7 times the quantity 3 minus 2x, easy, right? Differentiate term by term and distribute the negative 3/7, right? So what does that derivative end up being, actually? Right? Derivative of 3 is 0. So if I just multiply it out, then I end up with y front, 6/7. Okay. So I rewrite that one.
Now we're with 5 times x to the negative second.
Good. Power rule, right? Really good. Okay. Oh, you're done.
Wait,
Really?
could we just do that? You can't put the top and then use the multiplying rule instead?
Okay, here's,
Negative x.
I thought I was done. Oh, you got a question here. What could I do?
Could you just, like, move all, like, if you had polynomials on the bottom?
You could.
Move them up to the
You
top?
could. So you could, but here's the problem you're gonna run into. So say you had, well, in about, I don't know, 3 or 4 days, you'll have an answer to this. But what if I had, it's a good question, what if I had something like x squared minus 3x over 4x cubed plus 1, something like that. So the suggestion is, could I write this as the product of x squared minus 3x times the entire bottom to what? Negative 1. That's great, but how do you deal with, oops, I deal with that one, derivative of that? You can't, you don't know how. You will, shortly, it's called the chain rule, but you don't know it yet.
Dealing with that? Just that part of it?
You guys can't take the derivative of that yet.
Distribute the negative 1.
You can't, because you can't distribute to negative 1. A plus b to the m is not equal to a to the m plus b to the m, right? That's only for products, okay? So you can't do it. You got to do it. The problem is it's a composition of functions. You have a polynomial to a power, so there's 2 layers to this. You don't know how to take derivatives of multi-layer functions yet. That's coming very soon. Good question, though.
Or read your textbook. Okay.